In this lesson, we are going to continue our discussion about variable selection in terms of looking at the step selection procedures. These procedures were more popular years ago when we didn't have the computational power to look at the best all the subsets and then choose the best one based on certain statistics. As a kind of preface before we get started, I typically use these methods to help us develop intuition of which variables could or could not be important. It's typically more popular and best practice to try and look at all the subsets, but there are some limitations which we'll talk about in our next lesson. So we're going to use our cement example from lesson 14A, and we're just going to go through and talk about how forward, backward, and stepwise selection approaches work. So recall, in our example, we had 4 chemicals that we were interested in whether they were important or not in helping us to understand the relationship with our heat or our Y. So also as another statement, there are a lot of different selection criterion. So when we're building our model, we need some way to decide whether we should keep or not keep certain variables. In this lesson, we're going to talk about a p-value approach. Now, the p-value approach is not the most liked approach, but the reason I'm taking the p-value approach is because we've talked about p-values before in this class, and rather than introducing a new statistic, we're just going to use the p-value. Now, with that in mind, JUMP and R both can use these methods using criterion such as AIC and BIC. I'll briefly talk about those in the next lesson. But the whole idea is I want you to understand at least the algorithm behind these selection processes and also know that there's different criteria that you can use. Okay, we're going to take a p-value approach because I think it's the most simple to understand when we're first learning. So the forward selection approach follows as we're going to specify an alpha level. Typically, you wouldn't want to pick 0.05. JUMP has a default of 0.25. We're going to be using 0.15 just so that you know you can change that alpha level. But what you're going to do is you're going to start off with a null model, no predictors. Then we're going to check if any of the out variables, so the variables out of the model, are significant compared to our alpha level. Then we'll put that variable into the model, and we'll just keep repeating 3 and 4. Let's go to an example. So in our forward selection process, what we're going to do is we're going to start off with the null model, which would be this. So this is just our intercept, okay? What we're going to do is we're now going to create 4 models, one with x1 in it, one with x2, one with x3, one with x4, and we're going to get the p-values related to these models. Then we're going to choose the p-value that is the smallest, but then also still under our alpha level. So in this case, our variable 4 is our smallest p-value, and it's under our alpha 0.15. So we're going to say, yes, we want to include this variable, okay? I'm going to jump quickly over to JUMP to maybe help demonstrate this a little bit more of exactly what I mean. So here in JUMP, we have our cement data. When I do fit analyze by Y, this is not how you're going to do it in your homework. This is just to do a quick way to fit all 4 of these models. So notice that we're fitting all 4. Fit line, and it's going to give us our linear fit, and here's a p-value for that model. We're going to follow this quickly through. And when we do this, we're going to get these p-values. So this 0.066 This 0.0006 is the 0.006 that I highlighted in your notes. You'll also notice that we have a p-value of 0.0598 for our variable 3 in our notes, and that's where these values are matching. Okay. So now that we said variable 4 is important, we now have to reiterate. So now this is our current model. And what we're going to do is we're going to test, given that x4 is in the model, what is x1, what is x2, and what is x3. So what this is going to look like is we're going to fit yi equal to beta naught plus beta 4 x4 plus beta 1 x1 for this model. And we're going to get that p-value. This, we're going to fit beta naught, beta 4 plus our beta 2, figure out what the p-value is. Then we're also going to do the same thing with the third x. Okay, we're going to look at our p-values. We see that this one is smaller. That's why I put the double arrows to tell you that this one was smaller than this one. And so because we have a small p-value and that p-value is smaller than our alpha, this variable, variable 1, now enters our model. Okay, we're going to iterate through this process again. So our current model now contains beta 1 and beta 4, and we want to check if we should add x2 and x3. So same process where this right here, this p-value is coming from fitting a model yi equal to beta 0 plus beta 1 plus beta 4 plus beta 2. There would be your x's in there, but for kind of room, I couldn't write that. So when we look here, we have a small p-value. This is the smallest one, and it's still smaller than our alpha of 0.015. So we're going to include this in our model. Now our model is beta naught, beta 1, beta 2, beta 4. We're going to run the procedure again, where we're going to put our beta 3 or x3 into the model, and we're going to look at that p-value. Notice this p-value is not smaller than our alpha, so we stop. And our model based on forward selection using the p-value criterion will be this model right here. Okay, where we're going to be including predictor variable 1, 2, and 4. So that's forward selection. Notice that once we put this whatever variable it is in the model, it is never going to leave that model. Also notice that when we are creating these models, they're not independent of each other. So x1 will have a different impact on the model given that x4 is in the model. And we notice that because if we look here at this value right here, this is the model at just x1. If we come down here, we see that the p-values are different. And so the impact of x1 given x4 is different than just the impact of x1 in the model by itself. So we know our variables are not independent and they depend on each other. Okay, so that's forward selection. We start off with nothing in the model, essentially. We check every single predictor by itself. We pick the one that has the smallest p-value that is also lower than our alpha. We add it, and then we repeat that. Backward elimination is literally the opposite way of forward selection. So again, we're still going to have to specify our alpha, but instead of starting off with the null model, we're going to start off with the full. So we're going to start off with all the predictors in there, and then we're going to check whether they should or should not be in the model. And we're going to repeat this. So note on the other page, I wrote that our alpha is equal to 0.15 for removal. So the whole idea here is that we're going to start off with the entire full model, and we're going to calculate these p-values. These p-values should look very familiar, and these are also known as our partial tests that we talked about last time. So let me go over to Jump real quick and show you how I got just those values. So we're in Jump. we would go to analyze, fit model. This is something that we've seen in our last lecture. Add all these, run. And so in here, we would scroll down and we would have this test or this table, and we'd have all these partial tests. These values, you'll notice, are the exact same ones in our notes. Okay? So let's get back to kind of the process of backward elimination. So we start with everything in the model, and then we check each of the values given the other ones. That's why it's a partial test. We notice that here, we want large p-values. We want to be able to kick certain variables out of the model. So in this case, our x3, given everything else, this value right here, is our largest. And so we're going to remove x3 from our model. Then we're left with a model with our beta 1, beta 2s, and beta 3s in it. We're going to do the same idea. We're going to look at x1 given the other two variables, x2 given the other two, and x4 given the other. We're going to look at these, and we're going to see which p-value is the largest and also larger than our alpha. So we look here, and we see we have a large, this is the largest p-value. So let me highlight that. This is the largest p-value, and it is also bigger than our alpha equal to 0.15. So we're going to remove that x4 variable from our model. So now we have the model with our intercept, beta 1, beta 2. We're going to look at our partial tests, and we're going to see that both of these p-values are small, and we're going to stop our algorithm. They're small, and they are also smaller than our alpha level. That's why we're stopping. So the best model based on backward elimination with an alpha of 0.15 is our model with beta 1 and beta 2 in it. So hopefully you guys have already noticed that our final model produced by our forward, which was this one, and our final model produced by our backward, which is this one, don't match. In this case, maybe differing by one variable might not be that big of a deal, but in models, as we start getting more and more predictors, if our models were to differ by a lot, then we would probably have this thing called multicollinearity. And we'll talk about that in lesson 17, but just as a hint and a foreshadow. Okay, so we had forward selection, where once we added the variable, it stayed in the model. We had backward selection, which was once we removed a variable, it stayed out of the model. Now what we're going to talk about is kind of a mixture of the two, or stepwise, or sometimes called mixed selection approach, where we're going to kind of be going back and forth of entering and removing the certain variables based again on this p-value criterion. So rather than going through this algorithm, because I know you guys can read, what I'm going to do is we're just going to go straight to kind of our pictures of our stuff. Note again that our alpha, just to be clear, is for entry and removal is going to be 0.5, keeping it simple. Okay, so the first, how we start with stepwise selection is we're going to start off with our null model. So this is going to look exactly like our first step in forward selection, where we're going to look at all four of the variables by themselves in the models. We're going to pick the one with the smallest p-value, and we're going to enter it. Now, when you get here, this is going to be a little bit similar to backwards. Given that x1 has entered, given that x4 has entered the model, do we need this x4? Because this is the first step, this kind of check step really doesn't make sense, but it's still there to kind of have completion of notes. We just added it, so of course, this and this would be the same. Let's go to our second iteration. So in our second iteration, we have beta 4 in the model. What we're going to do is say, given x4, how does our model look now with x1, 2, and 3? We're going to pick x1 because it has the smallest p-value, and that p-value is also smaller than our alpha of 0.15. So we're going to say, hey, variable 1 can now enter the model. How stepwise differs from forward and backward selection is now we're going to check it. So what we're going to look at is the model. Given that x4 is in the model, how does x1 play? And given that x1 is in the model, how does x4 play? This is similar to our backwards selection. Now we're trying to see, can we remove one of those given the other one? We can notice that no, we cannot, because our p-values are low and they're also smaller than the removal alpha of 0.15. So we're going to keep both 1 and 4 in our model. If we go to our third iteration, we're going to do almost similar to the forward approach, where we're going to look at which one we're going to add. We have a p-value of 0.05, which is the lowest of these two. Then we are going to also check that it's lower than our alpha of 0.15, and we're going to add variable 2 to our model. Now we're going to look if we can remove any of the variables. So here's our backwards, air quotes, step. And when we run our analysis for these of each variable given the other, you guys are going to notice that our p-value of x4 given x1 and 2 is large. Between these three, this is the larger one, and this is greater than our alpha of 0.15. So we're now going to remove this x4. Okay. This is where, again, stepwise is different. x4 was our first one that we put into the model, but now what is being said essentially is that given x1 and given x2, we don't really need x4. Then we come back here to our next iteration where we only have beta 1 and beta 2. We check the p-values. These are larger than our alpha of 0.15, and so our algorithm is done, and our stepwise selection tells us that we want this model. Again, forward selection, once you enter the model, you can't leave. Backward selection is once you leave the model, you can't come back. Stepwise is kind of this mixture between the two, looking at it. In JUMP, these are the default significance values. I'm going to make you change them just so you know that you can for maybe your research. There is one thing I want to say, though, about these more classic approaches, is that they're not the end-all be-all. So hopefully you guys could potentially see that as we start getting more predictors, the forward, backward, and even the stepwise selection processes are going to be limited in what and how many and the different combinations of variables that are seen in your model. So typically, these selections, these stepwise selection procedures are used as a guiding light, or they're going to help develop your intuition of which variables should be kind of in the model and what you should be proposing. Then, again, the more modern technique is to use the best subsets method to evaluate a bunch of models, okay, and looking at all possible subsets. Now, in our case, we only really have 4 variables, which in reality or perspective to most data sets is pretty small, especially with the influx of information that we do have in our data today. And so I use selection procedures as a way to just kind of get an intuition of what may be the best model we're going to get from our best subsets method. The second thing I want to talk about is in our notes, we used the p-value criterion. I'm going to abbreviate criterion, okay? In R, my R users will see this. there really isn't a simple way to do the p-value criterion such as somewhere like jump. And so typically what methods use is AIC and BIC. I won't go into too much detail about what and how these are calculated, but these are other statistics that are used in maybe deciding whether we want to add or remove variables. Okay. And we'll get a little bit of practice of looking at these statistics in our homework and in the next lesson. With that, that concludes our discussion of the step selection procedures. Our next lesson, we're going to talk about the best subsets or all subset procedures, looking at different criterion.